So, okay, mute that. Good. So, today we're going to have a look at the first and second order system responses. Some of this draws on, of course, what we learned from the Laplace transform and some other things that we've been meeting as we go along. So this is just to formalize it and to know what to expect going forward, because it will come up from time to time again. So again, as you recall, and this is part and parcel of the revision a couple of weeks ago, that if you have a general form for a first order differential equation, and the first order differential equation, of course, simply means that we have a first order derivative of either the dependent or the independent variable, as the case may be, but the input and output, that you have at least just one, a dy dt or a dx dt, or a y and dx dt, and so on. Once you take the Laplace transform of this sort of equation, you'll end up with this form here. And you can separate it if we assume that the input signal is causal. Remember that word, causal, means that nothing happens before t equal to 0. If we assume that, then there are no initial conditions on the input, the signal. The output may or may not have initial conditions. We said that depending on what you're dealing with, sometimes you force the initial conditions to be 0, but it isn't always the case. And we know that circuits, for instance, that have capacitive or inductive elements in them hold energy. They will hold a voltage, they will hold a magnetic charge. And at the time when you do something to it, unless you took an active role in making sure that the inductors were discharged, that the magnetic field was discharged in the inductor, so it doesn't have anything to send back to the circuit, or that the capacitor voltage was set to 0, then you have to assume that there's some sort of initial condition around. And if you do that, then you land up with the Laplace transformed version of the differential equation, which is what we have below. And you can separate it into two parts. There's a part that has to do with the initial conditions, and there's a part that is only dealing with whatever the input is. All right, once you do that, so we have ys, which of course is the output response in the S domain. The initial condition response is the part that has to do with the initial conditions, and of course the input response. So the system starts somewhere. When you put an input on a system, the system starts somewhere and it proceeds from there. So that how it begins is the initial condition response, and then after that, now it responds to the input. So if y0 minus is 0, in other words, if we get rid of the initial conditions, we take an active effort or an active role in making sure the initial conditions are 0, then what we left with is the equation on the top. And what we said is that we define, well, your notes have derived, because what I did is to sort of combine the two bullets here. What we said is that if xs was delta t, an impulse, sorry, if xt was delta t, xs is equal to 1. And if xs is equal to 1, we call this bit that remains here, we call that the system transfer function. So the system transfer function, and we said it before, was the Laplace transform of the impulse response. So if you do that, then what is yt? So ys, when xs is 1, ys is in fact the transfer function. So ys will be equal to gs. So if ys is equal to this, what is yt? And this is where you do your little algebra. If it is of that form, then you have to find the inverse Laplace. And one of the things we said is that the order of the numerator and the denominator, that the order of the numerator has to be less than the denominator. If not, then you have to divide at least once, right? So this is all a bit of revision here again. So this is not, the order of the numerator is 1. The order of the denominator is 1 here. So the system is not proper. Excuse me a second. Yes, so because the order of the numerator is the same as the denominator, we have to divide at least once. If you divide, you're going to get some constant, and because this will go into this 1, which is a constant here, and then you're going to be left with a remainder, some b over s plus a. And if that is the case, then you can solve for both a and b in your normal partial fractions expansion. And what you will get is that a is b1 and b is b0 minus a1, ab1, right? And you go right back now. So if you have it here, you look up in your tables, the inverse transform of that is a delta of amplitude b1. And the inverse transform of this, so this is just a constant here, and this is an e to the minus at. Everybody remember that, right? I'm hoping so. If you're not following, let me know, right? But this is straight what do you call it? Laplace revision here. So at that point now, if you were to look at what the final answer is, if this is my response, if I sketch this now, notice b delta t is some impulse at t equal to 0 of height b1, right? Height b1. Forget my axis here. I needed to give it some fake values here in order to plot the graph, because b1, if it's an impulse, of course, is 0 with an infinite height. So I have no way of really plotting that on a graph. And then this now is a decaying exponent. And of course, the rate of decay is determined. It starts at some value and it decays at a rate determined by E. The important thing here is that notice, now this is the kind of response, a first order system, for instance, a simple RC network gives you that sort of behavior. If you turn it on, and you supply an input to it, the capacitor will attempt to charge very quickly, but the duration of the impulse is so short that the capacitor just charges very quickly, and then there's nothing else on the system. So whatever it happened to charge during that brief duration of the impulse just simply dissipates after a while, and that is determined by the RC constant for the circuit. So the important things to draw from this, first off, the impulse response of a first order system cannot be sinusoidal. In other words, there are no oscillations. Notice you're not seeing any behavior, you're not seeing anything looking like this. Here, you're not seeing anything doing this sort of behavior at all. Okay, so a first order system, anytime you encounter a first order system, the impulse response, there's no way the impulse response can give you a sinusoid. Okay, why that's important, we will come to both here and elsewhere. Okay, it's a way, and especially in your control systems and so on, you're going to meet these sort of things, and intuitively you will say, okay, it's a first order system. So if I put an impulse on it, I'm not going to get oscillations being created. Everybody following? Yeah. What about a step response? In the case of this step response, xt is ut. So xs is 1 over s. So again, you put in xs as 1 over s inside of here, and then you go through the process and you solve. If it's a partial fraction here, so this is going to be b1s plus b0 over s into s plus a. Notice at this point in, shucks, I should not put the brackets here. All right, so it will be b1s plus b0 over s plus a. Notice now that the transfer function is proper. The order here is 1, the order here is 2, because if I open this, I'll have an s squared. So now this is going to be some constant over s plus a plus some constant over s, and you solve for k1 and k2 as you're accustomed doing. If you do that, again, whatever that response is going to be, you're going to have two parts of the system again. You're going to have a part, this is for the step response, notice this is for the step response. You have an answer that looks like the system. Remember, the system transfer function is something over s plus a. All right? This now determines a transient response. And then there's another part that looks like the signal. Remember, it's a step response. So there's a something over s. This looks like the signal. This determines a steady state response. So remember we said you have a response looking like that. I just arbitrarily I'm drawing it. The transient response here, in other words, how it gets from where it starts to where it settles down, is determined by the system transfer function. So the system transfer function will dictate how it does all of this. Where it settles down after a period of time is determined by the form of the signal. In this case, it's a step, so it's supposed to settle down to some sort of value. Yeah? Make sense? So the answer has two parts, and if ever you come across here or elsewhere and somebody tells you, okay, put in an input on a control system and so on, what would you expect the transient response to look like? It means that you separate you separate the system into the part that is looking like the input and the part that looking like the transfer function. The part that resembles the transfer function, in other words, the part, remember we already said these things are the poles, right? The roots of the denominator, the poles. The part that has the poles on it is the part that resembles the transfer function, and that is if how the system will determine the transient response. Okay, and the other part, whatever the system input is, apart from an impulse, if it's a step or whatever it is, there will be another part that has as its denominator the Laplace transform of the signal. That is the one that determines how the system will be in its steady state. In other words, after it does whatever it has to do, as time goes on, it is going to eventually land up there. All right? So for instance, the RC circuit, if you do that and you just you just substitute the time constant, instead of putting 1 over RC, we just use tau, for instance, you're going to get the answer for the step response having two parts, the steady state response 1 over s, and the transient response, the minus 1 over s plus tau. So if you were to take the inverse transform of this is of course ut, and this of course is going to give you an e to the minus tau t. Okay, and therefore this is how the response would look like. The first thing, so the blue here, right? This is the ut, that's a part of the response. The e to the minus tau t is this bit here, right? Decaying. So when you add the two of them together, this is what the step response for an RC circuit would look like. And you know that we're just proving it what you know intuitively. If I have an RC circuit and I charge the capacitor through a resistor, when I put a step on it, right? Right? If I put a step voltage here and this is 0, then this voltage is going to, in response to this, the capacitor will charge until it gets close to whatever that voltage is, and then settle down and stay there. All right? And then if I remove this step voltage and put this back down to ground, the capacitor will discharge, and you know it will, if it charged up, it will discharge as an exponent. Okay? So that's our first order step response. Again, the main points here, notice there are no oscillations. So you're not going to see the final response doing all kind of things like that. Okay? The step response of a first order system also cannot be sinusoidal and also will not have oscillations. So both the impulse and the step response for these types of systems will just start somewhere and end somewhere, and that's it. No jumping around the place as yet. The second order systems is where the things start to get interesting. And there are many second order systems that will be encountered. So let's have a look at that now. The general form, of course, you have at least a second order derivative on the input and output, right? Assume that the input is causal. And again, we run the Laplace transform through this. If you run it, then you're going to get, again, the two-part answer. You're going to get the output response that is composed of a part that has to do with all the initial conditions and a part that has to do with the input. Okay? We can take care of the initial conditions under certain cases by making sure that we ground all the capacitors, make sure motors and whatever it is are all totally off when we start to do the testing. The transfer function of this, if the initial conditions are set to 0, you could ignore that. And if you want to find out the transfer function, xt is delta t. Therefore, xs is equal to 1. So if xs is 1, this is the transfer function of the second order system. A second order system, so notice is second order, so you're going to have an s squared in it. And therefore, by extrapolation, a third order system would have an s cubed, a fourth order would have an s to the fourth, and so you keep going on. So from now on, you automatically will know that, okay, somebody's saying we have a second order system, so. You know that the transfer function has an s squared somewhere in the denominator. So it's s squared or some as squared, and you have some other stuff in here, but you have an s squared in the denominator. So the transfer function looks like that. So let's see now how this thing behaves. And this is where it starts to get different than the first order system. If I give you this, and you can try this just to make sure, we have a system here where y prime, this is of course dy dt, is equal to y and some variable. And that variable as well, the derivative of that variable is also related to y and also x. So this is like, you have a system, you have y goes inside of here, right? It goes to something inside of here that takes y and gives you an output q inside, and then another part of the system that takes q and gives you x coming out. Okay? Fair enough? So the q is like an internal signal. What we are interested in is the relationship y equal fx. We don't care what q is, so we have to eliminate q. All right, and of course, to eliminate q, you have to substitute, you know what q bar is, so you could you have Q, you have Y. So the job here inside of here is to eliminate Q from this. So the first step, of course, would be, if I take another derivative of this, I'd get Y double prime is equal to minus 6Y prime plus Q prime. And if I have Q prime here, then I could substitute Q prime from this. So I'll now get an equation with Y and X alone. All right. The fact that I have to take the derivative of this to get a second order system twice means I'm now dealing with a second order system. Make sense? You're following what I'm doing? Yeah? Yeah, no, maybe. Good. So let's assume all the initial conditions are 0. So in other words, when I say all, that the input is causal and the system has been started from scratch. If you do it correctly, you should get something, an equation looking like that. Let's see how that behaves. The impulse response is x equal to 1. So if I were to take the partial fractions, I'm going to get that yt. The impulse response is a e to the minus t minus a e to the minus 4t. Right? E to the minus 2t looks like this. E to the minus 4t is something looking like e to the minus 2t, but decreasing even faster. So minus e to the minus 4t is going to be that flipped along the y-axis, which is this one here. And of course, the answer is going to be the difference between the two of them. So you get that red answer. Notice now, notice how you're starting to see some strange things inside of here. This is now giving you a kind of shape. You remember the step response for the first order system, or sorry, the impulse response for the first order system looked like this. It just went up and it came back down. Notice this one is doing us a kind of funny behavior now. It's starting to do this and it's settling down. But this clearly now is a different kind of behavior than this, right? And we want to see now what really could happen inside of here. This is looking different. So we're going to now spend the next couple of slides exploring that. All right? Everybody with me so far? It's straightforward. It's easy to follow. Just pay some attention. Good. So now let's generalize. So the same second order system like what we had here, right? Inside of here, I'm going to put a general form of a second order transfer function now. Get past this. So the transfer function for a general second order system is going to be some constant over s squared plus 2k a0s plus a0 squared. You'll see where all of this come in a while. So everything here are constant. This is a constant, this is a constant, and this is a constant. Okay, it's a second order system, so we have s squared. And now let's start to explore this now. Let's see what the step response looks like. So the step response is xs is 1 over s. If I put xs as 1 over s here now, okay, I am going to get just to simplify it here a little bit. So if xs is 1 over s, I'm going to get this by 1 over s. So I'm going to have, if I resolve this into partial fractions, I'm going to have something over s, and then something over s squared plus 2k a naught s plus a0 squared, right? I want to figure out this one. This one is easy, right? This is the input response that we know about. This is a part that's going to behave like this step. So this is easy. This bit now is to figure out this something when I resolve this in partial fractions over this bit here. So let's look at this here. This numerator here, denominator, sorry. I could express this is the denominator here. I could express it as s plus something into s plus something. In other words, I could try to factorize this. And that is easy, right? I could use my quadratic formula or complete this square. So this can be expressed as s plus a big thing here times s plus another little expression here. Notice the only difference between these two is this sign. Here's a k plus and here's a k minus. Okay, so in other words, the whole partial fraction expression is going to be a over s plus some b over this fraction plus some c over this fraction. And in other words, if I were to take the inverse, yt will be aut plus be to the minus all of this, right? Let me call this x, x1 and x2, be to the minus x1t plus ce to the minus x2t. Everybody following? Right, you could verify the algebra afterwards. I just want to make sure you're following what we're trying to do. So let's see now. We have it in that form. And so that the answer, which is what I have here. So notice the indices of the components. This one is e to the minus a, as we said, we were calling this x1 and x2. E to the minus a x1t and c to the minus a0 x2t. A lot of that now, the behavior of this, for instance, if x1 is positive, if x1 and x2 are positive, then this is going to be an e to the negative something t. This is going to be an e to the negative something t. In other words, if x1 and x2 are positive, this system will, this is a decaying exponent, this is a decaying exponent. If x1 is negative, then a minus here, for instance, if they are both negative, a minus here and a minus here is going to give me an e to the plus at, which is an increasing exponent. That is a system that will just keep going and going and going and going. And then, depending on what happens here, if the root of this is negative, if I'm trying to find out the root of minus something, then inside of here, I'm going to have a complex number. And e to the a j a naught t plus or minus e to the minus a j a naught t. That now is a sinusoid. You remember e to the j is cosine plus j sine. You remember that? Right? So let's see now, let's observe the effect of this. Notice that all of this depends on the value of k. And where was k? K is this thing here. Right? Everybody with me so far? All right. So let's see if k is less than 0. If k is less than 0, the first part of the answer, aut, is independent of k, so that doesn't matter. If k is less than 0, oops, have the animation a little wrong here. Forget the two bottom bullets for the time being. If k is less than 0, it means that this is going to be negative, right? And this If k is some value, k squared is positive, right? If k is less than 0, meaning that k squared is positive, so k squared minus 1 will be a positive answer. So this is not going to impact too much the overall answer, but of course, k squared minus 1 is going to always be less than k. So if k is negative, k squared minus 1 is always going to be either a positive or negative number less than k. So this whole thing is going to be a minus by a minus, so this is going to be positive here. Same thing for this one. The answer inside of here, this whole answer here is going to be negative. That now, therefore, means that the answer is going to be some a e to the plus a naught t, which is an exponentially increasing well, signal. I should have signal here. Just write out exponentially increasing signal. Not so much a sinusoid, but an exponentially increasing signal, and the system will just go unstable on you, right? Here was specifically if this turned out to be complex, but I mentioned that before. Don't worry too much about it. The answer is that if k is negative, right? Once k is less than 0, the output is going to be exponentially increasing. Okay, everybody with me?
Yes, sir.
Nice. So k less than 0 makes ys unstable. K greater than 1. The first term is independent of k, so we don't care about that. The second term now, if k is greater than 1, if k is greater than 1, meaning it's a positive number bigger than 1, here, this section inside of here is positive. Here is a small positive, will be a positive number, slightly smaller than k. So this bit here will be positive. Positive by negative means that the exponent, the overall exponent is going to be negative. Same thing here. K is a little bit bigger than k squared minus 1. So if this is positive, you're going to take away a small number that is a little bit less than that. So it will still remain positive. In other words, a minus by that positive is still going to give me a negative exponent overall here. So two negatives means that the output, this is independent of k. This is the e to the minus a t. So this is going to decay. Same thing here. All right, going to decay. So once k is greater than 1, the system is stable. K less than 0, system unstable. K greater than 1, system unstable. K between 0 and 1. Let's look and see what happens. The first term doesn't care. What about this? If k is between 0 and 1, depending on the value of k, this term here, right, could be complex. Likewise, this term here. So is that going to be stable or not? If it is complex, remember again, e to the j omega t, for argument's sake, I'm just putting it in that form, is cosine plus j sine omega t. Cosine is a sinusoidal signal. Sine, of course, is the regular one. Those are oscillations. So what a system that is giving me an output, remember there's a step response. If I put a step into the system and the system is giving me this kind of response, is that stable or not? Depends. Okay, so let's observe that a little bit further and now pick some values of k. So let's stick in here. You have the slide, so you could work it back out. I'm making k equal to -1. We already said if k is less than 0, the system is supposed to be stable. So plug these values inside of here. make A0 2, B equal to 4, K equal to -1. The step response XS is 1 over S. So if you do that and you plot it, notice that this system is unstable. Notice that after, in this case, after a second or about 1.2 seconds, the output is like about 65 units. If that was volts or something so, then this would clearly just going up to the VCC of the system. Or if it's an AC system, it's going to approach very quickly what the limit of the system is. This is not good, right? You don't want to have this at all. Take the same system and make K equal to 3. When K is greater than 1, we said the system is supposed to be stable. So we plug that inside of here. This is what we get. XS is 1 over S. Notice what's happening here. Right? So the system is a step response, and the system responds nicely. There's a step input, and it goes, and we have the transient stage here, which is where it's changing. And you could look at this now and see that the steady state response is at about, the amplitude settles down to about 4 units, whatever that happens to be. Remember, and this is a little revision, if you wanted to find what is doing here and what is doing here, you have the initial value theorem, AIVT, and you have the final value theorem that could tell you what the steady state response is going to be, right? So you could run that here, even if before you plot it, you could run it to see what the steady state response is going to look like. So in fact, the previous one here, if you were to run the final value theorem for this, you would probably get something over 0, telling you that it's unstable. It's going to have a very large number. If you run the final value theorem here, you're going to get that the final value is going to tell you as t goes to infinity, the system is going to settle down to 4. That's the kind of utility here. So you don't necessarily have to plot this graph to see that the system will be stable or unstable. So let's play around now with K between 0 and 1. If K is 0.5, we keep the same 2 constants as before. The transfer function becomes that. XS is 1 over S. You do the step response now. Notice what it's going to do. Now you can't get this, the final value theorem is going to give you this. So you really have to plot this, and I will show, we will run through that when we get a little chance. You could do this in MATLAB, right? Or you simply, when you get the time answer, remember when you do this, you could do the inverse transform and so on, you get YT equal to something, and then you plot it, put in values of T and plot it. Notice that the system is stable, but notice that what it's doing. So it responds, it starts, I putting a step input. This is a unit step here. So it goes past the value, it goes here, and then it's settling down. So it's bouncing along a little bit. It's stable, but there's some oscillation here. That is something called overshoot. And that's a very critical thing in control systems. For instance, if this was a robot, if this was a transfer function for a big industrial robot, and it's picking up something like an engine component or a vehicle chassis, and it's moving it from point A. So it starts here, and it's supposed to move the thing from point A to point B. What this is telling you is that it will pick up the engine chassis, it will move it, here's where it's supposed to end, but it's going to move past there, then come back, and then come back and eventually settle where it's supposed to drop. That is dangerous, because if you're dealing with, let's say you're dealing with a situation where you have a human operator somewhere here watching everything. You can't have the robot or a crane, whatever it is, picking up the component and going past the target spot before it settles and come back to where it's supposed to be. Yeah? Let's play with K a little bit again. If you put K equal to 2.2, sorry, notice now that you're getting even more oscillation. So in this case, if it was moving from point A to point B, it's going to go here, it's going to come back, it's going to go here, it's going to come back, it's going to go here, and then eventually settle down right here. All right, that extensive sort of oscillation is what you call ringing. There are some uses for it, but there are certain applications that you don't want. For instance, again, okay, let's say this was the steering wheel on a vehicle, right? If you turn it in one direction, the last thing you want is that the car will be drifting back and forth before it responds and settles down. All right? There are certain things that you might want this sort of response or step response for. For instance, music, if this was a transfer function for a system to generate a musical tone, this is the sort of thing you would want. It like when you ring a tuning fork, it will vibrate and then slowly die out. So if the system is of that nature, then this sort of response would be required. If it's something like a robot or the guidance system for a plane or a car or something of that nature, or a crane, you certainly don't want this. And let's make k equal to 0. If k equal to 0, notice what is going to happen. It's oscillating all the time, right? You're getting a sinusoid or a cosinusoid or oscillation. This is where it was supposed to settle down, right? It's supposed to settle down there, but it's going back and forth all the time. This is unstable, but is it unusable? It depends. As we will see in electronics, this is what a signal generator does, right? A signal generator will give you that kind of output, and you want that. But certainly you would not want the crane, as I was giving example, or if this was something where you're turning sending a signal to control the flow of natural gas in a processing plant. If you tell it to turn on the valve by a certain amount, you don't want to be, according to this will turn it on, turn it off, turn it on, turn it off, turn it on, turn it off all the time, right? So that kind of thing, depending on the situation, is not usable, okay? So it may be unstable, but usable or unusable. All right, so everybody following? So everything depends on this value of k, of this thing called k. And where was k? Remember, we had a thing, we had it as a0 squared over s squared plus 2k a0 s plus a0 squared. So k was right here, right? And as we varied, we kept k. Actually, I had a b. I think I had a b somewhere. I think it was b here, right? So I have some constants. So I fix these. I fix this. I fix this, and I was varying k. And in fact, as you can see, depending on the value of k, the system goes from stable to unstable, and it runs a gamut in between. You get the point where it oscillates back and forth and so on. So they have standardized that, and what they normally do, our equation here was, I'll write it here, was a0 squared over s squared plus 2k a0 s plus a0 squared. This is what we were playing with just now. It has been standardized in controls and signals and systems. So the standard terminology, in fact, is that this a0 instead, they call omega naught, and it's called a system resonant frequency. So they're standardizing, instead of a0, it's omega naught, and they call that the system natural resonant frequency. So it will under certain conditions, like here, it will oscillate on this frequency. The frequency of this sinusoidal signal here is omega naught. All right. And then k, they give k a special letter. This is a Greek letter zeta, and they call this a system damping factor. Damping, you remember from like the shock absorber system that you use in second order systems and so on. The damping factor, so if the damping factor is large, the system doesn't oscillate. You get a response looking like this. If the damping is very small, right, or negative, you get the system doing you that. And if the damping is between some values, which is 0 and 1, you can get the system giving you some overshoot all the way up to oscillating all the time. Okay? And we have some special terminologies. When zeta is less than 1, that's a damping factor, the system is underdamped. So you get a response, you get the sort of normal step response here. If zeta is too big, then it tends to give you this kind of behavior. So it's responding, but it's taking a long time to respond. This is underdamped. Right? Sorry. This is overdamped. Okay, the zeta is big so that it's taking a long time to respond. When zeta is less than 1, the system, depending on the value, could do this, it could do a little bit of this, and so on. This is underdamped, right? Right? And then when it is exactly equal to 1, we get it behaving just like this, where there's no overshoot, and we call this critically damped. All right, so underdamped is when you're getting a certain amount of oscillations. If it's severely underdamped, of course, you're going to get this thing bouncing all over the place. Overdamped is when it's responding, but it's going from the transient stage is very long, and then it eventually settles down. And then critically damped is just when it starts to behave like a first order step response, is just barely the hint of overshoot, and it's settling down. Okay. Yeah. So questions. We covered a bit here. The crux of the matter is the variation of that transfer function with K. All right, and once you understand that, then that's the takeaway from this lecture. The second order systems, a general second order system, has a form that has a frequency of oscillation and a damping behavior. If the damping is too small, the system will oscillate at omega 0. If the system is too large, if the damping is too large, the system will behave almost like a first order system. And depending on the value of the damping now, you can actually get the response to have a certain amount of overshoot all the way up to oscillating on a continuous basis. Okay? In many cases, you have some control over the damping. In other cases, you have to do other things that you'll meet that in your controls course, how to compensate for that. So questions? All right. It is maybe slightly heavyish to deal with, but go back over the lecture slides. You will have the recording for this, and listen carefully to what we discussed. And I'll show you also in MATLAB, maybe next time, how you could get MATLAB. In fact, has a step response. You could enter the coefficients, and you can evaluate how the step response for a system looks like. Right, so you could play along with this, but we will do it both mechanically, manually, and using MATLAB as we do some examples later on. All right. Okay, so let me stop the recording here.